So today hard problem, split array largest sum given integer n and k no, so split into k non-empty subarrays such that the largest sum of any subarray is minimized when we have 1000 elements and k is 50. That's binary search. We can binary search immediately, I think. So we binary search for the answer, because if a largest sum can be 10, it can also be 11, 12, 15, 20, whatever. And then to evaluate one option, what we do is, well, we take everything from start until we exceed that midpoint, right? So if midpoint is 10, first subarray is this, second is this, and then we find out how many we do. And if we do more than k, then we have to increase the midpoint, and if we do less than k, then we have to decrease the midpoint. So let's start by grabbing the node size. Okay. Worst case, we take all of them. So I need to get the sum is 10 to 9. So let's call this sum can be 0. I guess, yeah, and r is 0. So first we do r plus equals nums I, right? So that's the max it can have. We can do one subarray with the largest sum. And now while we do binary search, so we find the midpoint, which is the maximum largest sum of any subarray, right? And then we do, okay, so now we have to solve it. So int count of subarrays is 1, current subarray sum is this. If current over midpoint, then we want to do count plus plus, current is nums I. Okay. Current plus nums I is over the threshold. And finally we add 1. So and then current so we have to reset the counter to this, and then add the current element in there. Finally we finish the last subarray, which has not closed. Now if count is over k, then we need to adjust it down, right? So, and otherwise we stay there, and in this case we have to add plus 1 here, and finally we return this wrong answer. Okay. We want to minimize, so if actually if we have more, then we have to, well, this says if we have more, then we have to increase it so that more elements fit, and then we get less partitions. I have to adjust this plus 1, just a trick I learned. Great, this works. Boom. Wrong answer. Well, we have to use exactly 3. So else if let's do this plus accent is under k. Let's do this. So what this does is we find that 1 is enough. No, that still doesn't make sense. Minimum has to be let's call it nums 0 and then L min nums L minimum of nums L whatever, and then I can remove this. Let's see. Nums I. Okay, that's still wrong answer. Like that. Okay. Should pass now. Great. Okay. So I'm at 1 milliseconds and everyone else is at 0 milliseconds. So my time complexity is logarithm of this, which is n times 10 to 9 logarithm times n. Let's see if we can do better from the editorial. Dynamic programming, what? N squared m. What's m? Okay. Bottom up, that's the same thing. Binary search. And log s. Fair enough. Okay. So it was just easy problem, whatever. On the other hand, n squared times m is like 50 million, and my complexity is like 1000 times. It should be faster, I guess. So, but whatever. Binary search. So intuition. If we can partition the array into k subarrays with largest subarray sum of x, we can partition them into k subarrays with largest subarray sum of x plus 1, x plus 2, what algorithm should we use to solve this problem then? What algorithm should we then use to solve the problem? Let's binary search for the answer to check if we can split the subarray into k subarrays with the largest having a sum of at most m. We can simply iterate over the array and keep cumulative sum of current subarray and split it if we exceed if adding a number would cause the subarray sum to exceed m, we create a new subarray for it. If the number of subarrays needed to partition the array into subarrays with sum at most m is larger than k, we need to increase m. Since that will cause less splits, and vice versa. Am I saying it right? Okay. N log max, where n is the number of elements and is the size of the array, and max is the node to avoid note that the boundaries of initial search are L equals min nums x in nums x and r equals sigma nums in order to avoid impossible subarray splits, i.e. a number is larger than currently checked m. Cases when a number is larger than the currently checked m, where a number from the array, whatever, okay, is the sum of elements in space complexity. Not much actually. O1, since we only use a couple of extra variables to keep cumulative when doing the binary search, and calculating the cumulative sum and subarrays used. Okay. Okay, today luckily it was fast, so I can start working on the compiler. Goodbye.